Okay, guys, I hope everybody's all right. So there are a few more dynamic memory allocation functions, just like clear allocation function, clear alloc. It's just like malloc function, but in this case, it's accepting two parameters. It's accepting two parameters, how many elements and how many elements and the size of each element, okay? And it's returning an address for me. So it works like this. So I'm asking for 25 integers from the heap, and this is the integer size. Usually it's 4, okay? And what does calloc function do? Calloc basically allocates the space, 25 integers, and then resets each input for me, okay? So resetting means 0, writing 0 for me. If it was, let's say, double, in that case, it will point 0.0 for me, right? 0.0, which means 0 in which means 0 as a floating point number. If you have any questions, please type there. I will get back to you as soon as possible. We will use both, okay? I mean, if I don't differentiate, if I don't explain exactly, you can use both. Otherwise, you will pick the correct one. Okay, so this is how it works. Another dynamic memory allocation function is realloc function. In this case, usually while we are using our space in the heap, we need more space, larger space. In that case, we are basically reallocating our current chunk, and then we are not losing any data. It works like this. So let's say, first of all, we are asking from the memory 15 bytes, and then I'm using it. Okay. Right now, in that memory chunk, I have a message. Later, I decided to use or add more stuff. In that case, what I will do, I will reallocate same space with a new size. Okay. So it works like this. If there's a, I'm sorry, guys. Yes, if there is a space, we are extending that space, and then we don't need to copy or remove anything. If there is no space, okay, after this chunk, so we are basically generating another chunk and then copying everything from the old part, okay? And in this case, we need more space, so I can use it. So we are adding much more message to my new space, okay? This is how it works. Okay, memcpy function. Again, this is a dynamic heap function. It's copying some chunk of the data from source to targets. Okay, so this function is accepting 3 parameters. One is the source heap, target heap, and then number of bytes. Okay, first of all, this is my source and this is my target. Okay, and I have data in those guys. Those look like different. Okay. When I call this function from PS to PT, we are copying 25 integers. In that case, it's copying every integer, every byte to target. Okay. I can do this as well. I mean, if I don't need all the data, I may copy some chunk, okay, from let's say 5 to 5 elements. So it will copy only 5 integers from source to target. It will ignore the rest, okay? And that's it. Oh, kaydı. Ayor lokal kaydı açtım arkadaşlar. Kusura bakmayın, bu kaydı unutmuşum. Ama lokal kaydı açtım. İnternetten inşallah yükleyeceğim. Okay. So thank you. Memory set function. When we allocate a space during the runtime, we usually reset the space. Okay. What it means, when we allocate the space, in that space we have some junk data. Okay. We have something, but I don't need those guys because those are there, and my allocation function usually doesn't reset this. Okay. When I call memset function with 0, it's basically writing 0 everywhere in that, so m bytes. Okay. It's basically resetting the space for me. But I can do this way. I mean, if I type 5, so it will reset with 5 for me. And this is the number of bytes. Okay. So maybe in the middle of the program, we may need to reset or set my target memory chunk. In that case, I can use memset function. Okay, so we are done with the dynamic memory allocation functions. And stacks. So this is a new topic. We will learn only stacks today, and for the next class. So we don't have a class next week. Okay. Again, we don't have a class next week. So be careful with that. Stacks. We got to define stacks and then how to implement those with arrays and linked lists. Okay. So stacks is a high level data structure. We are able to insert and delete, and we are always writing stuff or data on top of the stack and reading data from top of the stack. So it's one way. That's why we are usually call it LIFO, which means list data is read first. So we are not reading in the middle. That's special kind of memory. Okay. It looks like this. It's just like a stack of trays or dishes. When we have more dishes, let's say green dish, we are basically putting that dish on top, right? We don't usually put it in the middle or at the very bottom because it's huge work. Okay, huge effort we need to do. And if we have one more dish or tray, we are basically putting on top. Okay, that's called push operation. That's the legal name for it. Inserting a new data to stack is called push. Okay. we are always writing or putting something on top of the stack. And when we read or use the dish, which is called legal name is pop, we are basically using the top dish first. And then if we need more dishes, we are getting the dish from top again. Okay, until the tray or stack is empty. That's why, again, stacks are called LIFO memories, which means last in, first out. Okay, we are able to implement stacks in two ways, with arrays and linked lists. First of all, stacks, there's a limit with the stack. We don't have infinite amount of memory. And let's say for the stack, top is the basically showing the index of the top element. Okay, and S is the index here. And then usually it's written this way so we can read it better. When we push new element, which is 3, we are basically writing 3 on top of the stack, if the stack is not full, by the way. And then we are incrementing the top index. Okay, when we pop a value from the stack, which means we are basically reading the top value, and then we are updating our index. Usually we are not removing the older 3 there, because 3 is sitting there. We don't care it is sitting. And if we need a new element, let's say 11, and system works like this. We are incrementing the top and then writing 11 on it, so we basically lose the older data. Okay, that's how it works. So when we read the data from stack, or when we pop the data from stack, we don't need to care to delete the old value. Okay, so 3 and 9 basically sitting there, but since my index is telling me that top index is 2, I only focus on here. Okay, and do you have any questions? Let me see. Okay, let's define a stack with arrays. Here's a limit, and we are able to write 100 integers in this stack at most. Okay, top is the index right now. So when we initialize a stack, when we create a stack, we are basically writing, we already have a space that it is holding 100 integers, and our first index is basically showing -1, which means it's empty. Okay, for is empty function, we are basically checking that if the stack is empty, again, if our stack top index is -1, which means our stack is empty. That's because we are in C, C++, Java, JavaScript, indices are starting from 0. That's why we are using minus here. Okay, push an element. So we have a stack here, and then we are pushing a new item. First of all, we should know that stack is not overflow, which means we have hundreds elements are sitting there, it's already full. We want to add one more element on top, but this guy tells me that there's a limit. That's why it's called stack overflow. Okay, again, if this stack is full and then we are trying to push a new element, we need to check that if it's full or not. Okay, if the stack was full, we are basically giving this message and we are returning. Otherwise, we are incrementing our index and then typing or recording the new item to that address. Okay, so pop, which means reading top element from the stack. First of all, we have an index, current index. Okay, and then we are checking that if stack is empty, we cannot read at all. That's why we are returning -1. Okay, otherwise we are basically decrementing the index and then returning the old value back. Okay, and top basically is reading the top elements. It's not updating my index at all. First of all, we are checking that if stack is empty, we got to say that stack underflow, I'm sorry, or stack is empty. Otherwise, we are basically giving the top element back. Okay, we are not removing anything, we are not adding anything, and we are not updating our index here. We are basically just getting the top element from the stack. Okay, when we create a stack, okay, this is a local stack. When we create a stack, we basically type the -1 for top. When we push any element, we are basically incrementing the index and writing our element to targets. Okay, that's okay. So in here, we are basically popping elements before writing anything. I'm sorry, we got to take this guy. I already fixed this. Yes, I already fixed this. So when we pop, we are basically printing 23 and our index becomes 1 now. We only have one element in the stack. So when we add two more, we are basically incrementing our stack. So as you see, we are always reading the final element, or we are always adding a new element at the very end. So we are not able to reach in between. Okay, so that's the beauty of the stack. And we are basically reading every element, popping and topping backwards. We are popping twice, so 22, 44, and then top element is 49. As you know, top is not reading or deleting anything. When we call pop again, now everything is empty. My index is -1. So when I call this function, it will say stack is empty. Okay. So any question? Okay. So let's say we are able to implement stacks with linked lists, just like here. In this case, each node is basically holding data for me, and then they're pointing the former value. At the very end, we have node here, right? Okay. This style is not a well known. That's basically electronic and it's ground basically. Okay, you should know that that's a null. So when we add or push a new element for a stack that is linked list, which means we are always writing new element on top. Okay, now top is basically pointing the new element. When we pop an element from the stack, we are basically getting this tree back and then updating my top index back to the older node. When we pop again, we are basically getting this 9, reading that 9, and then updating my top index. Okay, and what happens since, let's say, when I update this guy without deleting this guy, that means these nodes are sitting in the memory and it's called memory leaks, right? So never forget to remove those guys. Okay, I have a node, stack node structure, and item is the data, and then next is basically pointing the next element. And next here will be null, which is basically the final one. Okay, okay. So let's say when we create a stack, what we do, we are basically making our stack top null. Okay, so I have a top index and then right now it is null. Okay, when we create the stack, basically, when we check that if the stack is empty, what we do, we are basically checking that stack top, which is my global index to stack, is null. That means the stack is empty. Okay, so when we push a new element to stack, first of all we need to generate a new stack node. Let's say my top was null, right? Remember, top was null. Let me put null here. So we have a local x node x, and x is basically generating a new stack node for me, and I am writing item, new item. Let's say new item is 5. I'm writing 5 in here. What happens? Be careful. So x next becomes stack top. So x next, which is here, becomes null, and top becomes x, which is, yeah, which is this. Okay, okay, now I have one element, top is pointing my first element, and then I'm done, which is there's only one element. Okay, when we pop from the stack, first of all we always check that if it's not empty, otherwise we are trying to read from empty stack. Okay, first of all, we are generating an empty node and item, and we are getting the data. Let's say I have these two elements, and this is node. Okay, and this guy is pointing this guy, and then my stack is pointing, stack top is pointing this guy, top. Okay, what it does, first of all, my temporary is holding this guy or pointing this guy. And then stack top becomes the top next, which means stack top is this, it becomes this. And what happens? Basically, I just lose this data by freeing it. Free temp. Okay. And free temp because freeze this chunk for me. Do you have any questions? Top from the stack. Again, top is not updating any value. It's basically reading the top element or final element from the stack. If the stack is empty, we are not able to give any data. Otherwise, we are getting the data. Okay, we are getting the item from the current top. Okay, it works like this. First of all, we create stack. Now top is -1. I'm sorry, top is null. And we are checking that if it's empty. In this case, top is null and it looks empty. That's why we will have this message. When we push two data, 49 and 23, so 23 will be right later, 49. Okay. When we pop the element, we are basically reading 23, and then now top element is 45. Now we are pushing two more elements similarly. Okay, and then we are writing the elements from the stack reverse. Okay, okay, stack is a very complex and valuable or great data structure we are using in compilers, and we will use in many applications. Even our programs are using stacks every time. Each of the program is using stack. Okay, compilers are basically parsing these chunks, okay, trying to understand the math behind it. So what does it do? It's basically reading parentheses, okay? And as you see, we have 3 opening parentheses and 2 closing parentheses. For C, this is a problem where we are going to close these parentheses. Right here, we don't know. Right here or at the very end. Since we don't know, there is a problem. But in some programming languages, just like Fortran, they will accept it, they may accept it, and we are basically writing at the very end. So they don't think that it's so much harder. Okay. So balance checker, this syntax check is basically is using stacks. Okay. How it works? First of all, we are generating an empty stack and start reading symbols. If it's an opening symbol, we are pushing onto stack. If we put this closing symbol, we are basically removing the parentheses. Okay. And what else? Okay, this is high level usage of stack that we are using every time, everywhere. Let's say I have a program. In main function, I'm calling f. In f function, we are calling g. In g function, we are calling back f again. So when in my main function, when I call f2, 3, so 2 becomes here, 3 becomes here. And then there's a return address, let's say 100. And then we are basically writing the local element, which is a, and sitting here. Okay. If the condition is correct, which means we are returning, and then we are not doing anything, we are basically removing everything back to home address. If not, we are calling GA, right? Yellow, and then it has Z, parameter Z. So we are sending, let's say 2, 3, this is 2, Z is 2, okay. So we are defining local variables P and Q. As you see, P and Q are sitting in the stack. And if we are not stopping there, we are calling f function again with new stuff. So this is P and Q and harmony. Okay. That's why stacks are important. Stacks are inevitable. So for a program, let's say for main, we are in the main function, we can call P1. P1 function may call P1 again. This is time elapse, I'm sorry. That means after P1 call, when we call the function, P1 function may call itself. That's basically recursive. Let's say somewhere here we return back and we come back to main function again. So when we come back to this address, we are calling P2 now. In P2, we are able to call P1 again. Okay. And in P1, we may call P1 again. Okay. And that's it with this stack. We don't see queues in this class because it will be huge for you. And I think we are done. Sorusu olan var mı? ilk projeleri toplamadı mı hoca? Ben birkaç örnek gönderenler olmuş ama. Cuma günü son. Evet. İnşallah. Evet arkadaşlar. Lokal kaydımı durdurayım.